Well, we're now on section 20.3, Voltaic cells. And after doing all of the oxidation reduction chemistry in sections 1 and 2, you may be wondering, wait a minute, I thought this chapter was about electrochemistry. Well, we're finally getting to the electrochemical part. We had to do that oxidation reduction stuff because we end up using oxidation reduction chemistry in electrochemistry. So we're going to be looking at an oxidation reduction reaction. Here we've got zinc reacting with copper 2 ion, and it creates zinc ion and copper metal. Now you can tell this reaction proceeds because the zinc is a silverish metal. The copper 2 ion is a distinctive blue color. The zinc ion is colorless, so you'll see that blue fades over time, and that the copper metal has a brown color to it. It looks black underneath that blue solution, but it has a brown color to it. And so we will find that this is a spontaneous process. And in fact, if you took General Chemistry 1 with us, you saw this particular chemical process in that semester. So we did that in the lab. So what we want to do is we want to say that is a spontaneous process. So zinc plus copper 2 ion is spontaneous. However, if we react zinc ion with copper metal, that is not a spontaneous reaction. So if we try to do that reaction, no reaction will occur. Just like if we have a ball and let it roll down a hill, that is spontaneous. Well, the ball rolling up the hill is not spontaneous, and that's exactly what's going on here. So this would be an uphill reaction. If you remember, back in chapter 4, we have a way of predicting whether these kinds of reactions can occur by using something that we call the activity series. The activity series is just a list of metals, well, a list of metals and hydrogen that have varying levels of activity, which just means reactivity. And so this is just a subsection of it, because we're not going to talk about the activity series, at least not extensively, other than to say a metal will react with an ion that is below it on the activity chart. So as you go up, the metals are more reactive. As you go down, the metals are less reactive. So zinc will react with copper 2 ion, and copper will not react with zinc 2 ion. And that is one of the things that we learned from the activity series. Well, in this chapter, what we do is we graduate beyond this and move on to applying real numbers to this so that we don't have to look at a chart. So that is kind of cool. Now, I want you to think about what does a spontaneous reaction mean for delta G? And hopefully you remember this. I'll give you a second to think about it. Okay, well, hopefully you remember this, that spontaneous reactions have values of delta G that are negative. And so we'll find that the reverse reactions will have values of delta G that are positive. We're going to talk about the delta G in a lot more detail, but and at a later point, but it's possible that we can take some of that delta G and turn it into work. And so we could potentially extract some of this energy in the form of work. But to do it, we need to be smart about it. We need to set up our reaction in a very clever way. And the way that we're going to set it up is with a voltaic cell. So voltaic cells, if we set them up properly, they can do work. Now, we are going to be looking at the same oxidation reduction reaction we looked at a minute ago. Here we've got zinc and zinc ion, and over here on the right we've got some copper and copper 2 ion. What's important here is that we are separating out the two reactions, and we're going to transfer the electrons from where the oxidation occurs over to where the reduction occurs. But in order for those electrons to move over there, they have to go through a wire circuit. And as they go through that wire circuit, they potentially could do some work. So as they flow through that external device, they can potentially do work, which here we just have a multimeter, which is measuring the potential energy difference. But we could potentially have something like a fan or a light or any number of things where we're harnessing some of that energy. And when we harness that energy, what we're doing is we're creating a voltaic cell. Batteries, this is essentially a battery. Batteries are so ubiquitous in everyday life that we don't even think about this, but we're constantly using batteries by converting the energy we get from chemical reactions into electrical energy. So very cool process. That energy is going to be the delta G, so we can harness that energy in the form of delta G and do work with it. As you'll remember from the last chapter, that delta G is equal to negative W max. So we can get up to that same amount of energy, but no more. We can't have more than that. In reality, it'll always be less than the delta G because we can't have 100% efficient. But that's neither here nor there. So now what we want to do, and there one more thing about this page is you'll notice that on that multimeter, it's got the number 1.10, and that tells us that the cell potential for this is 1.10 volts. That's the difference in potential energy between our two electrodes. So 1.10 volts. Well, we're going to talk about what a volt means here in just a few minutes. So let's take a closer look at this voltaic cell. So here is a drawing of our voltaic cell. We've got, this is the zinc electrode. And at that electrode, zinc is getting oxidized to form zinc 2 ion plus 2 electrons. So that is happening at the surface of that electrode. Since this is where oxidation is occurring, we refer to the electrode where oxidation occurs as the anode. So oxidation always occurs at the anode. If we were to get microscopic glasses out and look at what's happening on the molecular level, well, here we have a zinc atom. It loses 2 of its electrons, and those electrons stay with the metal and go up the circuit. So they're going to go up that electrode. And the zinc ion is going to float away from the zinc electrode. That means that over the course of time, if we let this reaction go for a while, this zinc electrode should get lighter. And that's perfectly normal. So our zinc electrode would get lighter. So that is the zinc. Now, because electrons are coming out of this electrode, we refer to it as the negative electrode because electrons are coming up. Well, those electrons will flow from our anode through our circuit over towards our cathode. At the cathode, the reaction that is going to be occurring is going to be copper 2 reacting with 2 electrons. Now, one thing that I want to point out is that when this oxidation occurs, we don't have to wait for some period later for the electrons to react over here. These happen simultaneously. So at the same instant that 2 electrons are being produced here and moving up the wire, 2 different electrons are being used up over here. That way we have a constant number of electrons that are in our circuit. All right, so there we are reducing the copper 2, and we call that the electrode the cathode. Reduction always occurs at the cathode. And then the reaction that's occurring at that cathode is that the copper ion is getting close to our electrode here, and then 2 electrons come over to it, and it picks up those 2 electrons, and it turns that blue copper 2 ion into a copper atom. And that copper atom is now stuck to the electrode. And so we will find that over time that copper 2 cathode, or the copper cathode, will start to get heavier. So it will gain mass as time goes on. Now, a couple of things. As far as the sign of the cathode, we're always going to refer to it as the positive sign. And there's an interesting story behind that. All these electrodes, these systems, these voltaic cells, were figured out long before the electron was discovered. And so initially scientists thought that it was actually positive charge that was flowing this way. It turns out for math purposes, it doesn't matter whether you think it's positive charge flowing this way or negative charge flowing this way. It all works out the same anyway. But that's why we talk about the negative charge flowing this way and instead of having the positive charge flowing this way. Another thing that I want to point out is that way back when I learned this in high school, back in a long time ago, I'll just say a long time ago, way back when I learned this in high school, I found, I was told that a way to remember, a mnemonic to remember which thing is the anode and which is the cathode, is that oxidation and anode always go together and they both start with a vowel, and that reduction and cathode always go together and they both start with a consonant. So I now must mention one final component of this, and without this component, this circuit doesn't work. And that component is the salt bridge. The salt bridge allows us to not build up excess charge in one place or another. If we have electrons flowing from this beaker over to this beaker, then this beaker on the right would be getting more negative. Well, that's not what happens. What actually happens is we get an equal amount of negative charge that will flow this way in the form of anions. So what this salt bridge is, it is a tube of glass, and inside that tube you put a strong electrolyte like sodium nitrate, one that doesn't participate in the reaction, that's going to have no negative effects on the reaction, but does allow electricity to flow through the solution because it is a strong electrolyte. So really all you need is something that is a strong electrolyte that doesn't interfere with the reaction. Usually it's fairly high concentration, and we'll find that usually what we'll do is we'll cap off the ends with something like glass wool or fiberglass, if you want to think of it that way. All right, let's look at number 22 on the in-class assignment. So I'm going to switch over to number 22 here. So there we go. So we've got a voltaic cell similar to the one that we were just looking at. One electrode compartment consists of a silver strip placed in a solution of silver nitrate, and the other one has an iron strip placed in a solution of iron 2 chloride. So it turns out here nitrate and chloride, those are spectator ions. The overall cell reaction is given below. So the first thing we want to do is we want to figure out which half reaction is occurring at the anode and which one is occurring at the cathode. To do that, we just need to figure out what's being oxidized and what is being reduced. So here iron has an oxidation state of 0, silver is +1. Here we've got iron is 2+, and silver is 0. So iron is going from 0 to 2+. That means iron is getting oxidized. Oxidation occurs at the anode. So we will have Fe solid getting converted into Fe 2+ Aq plus 2 electrons. And then the reaction that's occurring at the cathode is that we have a silver ion getting converted into silver metal. So I'm going to write silver ion Aq plus an electron, and that gives us Ag solid. Now you'll notice that we have two silver ions getting converted into 2 silver atoms, and there it would take 2 electrons to do that. But I am only writing down the simplest form of this equation for the reaction that occurs at the cathode. I will explain why that is here a little bit later. But those are our 2 half reactions. So next, we want to sketch the voltaic cell. We're going to use the diagram that we saw that I just shown you a little bit ago, kind of as a model. And usually we'll write the anode on the left side. So we'll put a compartment for the anode here. and a compartment for the cathode adjacent to it. So we'll call this one the anode compartment, and this one the cathode compartment. All right, let me make sure I've got all that on the screen. Okay, so there is our anode compartment and our cathode compartment. The anode is iron, so we'll put the piece of iron, since we have a solid there, that is our iron anode is there. So that's our iron anode. We have a solution, and inside that solution we've got iron 2. So we'll have Fe 2 plus AQ. All right, and over here at the cathode, silver. So there's silver metal in there, so we can have that as our cathode. So we will indicate that we have Ag cathode. All right, and we've got some stuff in solution, and the important part of that solution is that we've got silver ion. So Ag plus AQ. So Ag plus AQ. All right, so let's see. Sketch the voltaic cell, anode on the left, cathode on the right. Okay, let's connect this up, and we've got some sort of thing here, like a multimeter. We don't know what the cell potential is, so I'm just going to put a meter here. All right, and then this will connect over here. So these are just wires that connect to our electrode. And it's not quite done because we need a salt bridge. And here I'm just going to draw a tube to indicate our salt bridge, and I will just label that as salt bridge. So there is our salt bridge. And usually at the end of the salt bridge we've got like a little bit of fiberglass that holds that salt in there without it letting it mix with all the other stuff. Okay, so now let's see. We want to sketch the voltaic cell. Label the anode and the cathode. So we've labeled the anode and the cathode. The sign of each electrode, just as a reminder, our anode compartment is negative because that's where the electrons are coming from. Our cathode compartment is going to be positive because that's where the electrons are going to. The electron flow will be this direction, so the negative electrons will flow this direction through our circuit. And the direction of anions and cations flow. Now this is pretty easy as far as anion and cation flow. Anions are going to flow towards the anode. So I'll put anions towards the anode. And then here I'm going to pick a different color. The cations will flow towards the cathode. So our cations will flow the opposite direction. So if it ever asks which direction do the anions and cations flow, anions towards the anode, cations towards the cathode. And I'm going to look here real quick and see if I have missed anything. Look at my notes. I think we're good. Okay, so that is number 23. So we're going to go back and go to the next part. And the next part, we're going to look at cell potentials. And with cell potentials, we're going to be looking at first what the definition of cell potential is. Now, if you look on problem number 20.25 A, it says what's meant by the term cell potential. Well, this is the answer to that. So cell potential, it's the difference in potential energy per electrical charge between the two electrodes. All right. Sometimes we will call the cell potential the electromotive force. So if I say EMF or E, all right, that will be it. And sometimes we'll even call it the voltage, although that's mostly, you'll see that in electronics, they'll call it voltage. All right. And then here, our definition of a volt is 1 volt is equal to 1 joule per coulomb. Well, joule is the SI unit of energy, and a coulomb is the SI unit of charge. So a joule per coulomb is our official SI unit for cell potential or potential. And we use volts for all kinds of things. And then here we'll find that this particular voltaic cell has a cell potential of 1.10 volts, meaning 1.10 joules per coulomb of electricity that flows through that circuit. So number 25, in case you're wondering, so number 25, here is number 25, and the answer to number 25 is that stuff, and I've already written it down, the cell potential, the difference in potential energy per electrical charge between the two electrodes, and then part B is what's the definition of a volt? 1 volt is 1 joule per coulomb. I'm not going to stick on that because the definition is right there. Okay, so now we want to look at electromotive force. This is an analogy for electromotive force. It is just a way of thinking about how this works. So we can think of a voltaic cell kind of like a waterfall. So here we've got whatever chemicals are making up our voltaic cell inside of this battery. And our electrons are going to come out of our anode at a point of high potential energy, and they're going to flow downhill to our place of low potential energy, which is where our cathode is. Well, for this waterfall, water will flow from this high potential energy at the top of the waterfall down to this low potential energy where the river or the lake or whatever is. And so it flows from high potential energy to low potential energy. Now, what volts tell you is not what's the total amount of energy of that waterfall. That's not the case at all. What this tells you, what volts tells you is how much energy per unit of electrons. And so we could think of it as how much energy per milliliter of water does this have. So if you had 1 milliliter of water, which is not very big, you had 1 milliliter of water up here, how much potential energy does it have because it is this height above the bottom? And that is the idea. Whereas this, instead of milliliter of water, the unit is a coulomb of charge. So we will find that water flows from high potential energy to low potential energy. The electrons also flow from high potential energy to low potential energy. All right, so now we want to look at something that we call standard reduction potentials. And standard reduction potentials we use these to calculate standard cell potentials. So standard reduction potentials, there is a table in Appendix E that has a more complete list of reduction potentials. And in that list of reduction potentials, they are listed alphabetically by symbol rather than ordered by the actual reduction potential. You'll see that we have a wide range of possibilities here from 2.87 down to negative 3.05. And that is our range of reduction potentials that we know of. So that is our range of reduction potentials that we know of. Like I said, we can use this as a way of calculating what the standard cell potential is. Now, in doing this, we need to have some point that was arbitrarily defined as 0. And they could have picked any number of things, but the thing that they decided to pick was something that you can reproduce anywhere. Because everywhere where people were doing chemistry or physics, they had acid. And so if you have acid that's at 1 molar and you have hydrogen gas that is at 1 atmosphere, then you can create the standard reduction, the standard hydrogen electrode. And we'll talk about that here in just a moment. Before I do that, I do want to go over to Appendix E so you can see the more complete list. So here is a more complete list. So So this is the it takes up a page and a half, and it's double columned. So I mean that's a pretty long list. You'll also see on this list that it is not listed in order of reduction potential. It is listed in a sort of pseudo alphabetical order based on the symbol, not the actual name of the element. So there you go. So that is our standard reduction potentials at 25 degrees, and then again there's the other part of this. We're going to refer back to this numerous times, so we will I will leave this open, and we will come back to it many times today. All right, so those are our standard that's our standard reduction potentials, and again they are all related to hydrogen. Now if at some point back when they were coming up with this, if they had picked some other point that they decided was going to be the standard reduction potential, maybe they wanted to pick oxygen instead, well then all of these numbers would have shifted by 0.40, and we would have just had different numbers. That would have been a weird choice, but it is technically one that could have been done. So taking a closer look at what the standard hydrogen electrode is, since it doesn't have a metal in it, we use a platinum wire. So we'll see platinum wire here and a platinum electrode. So the reference is called the standard hydrogen electrode. Sometimes you'll see people refer to it as SHE or SHE. We'll see that by definition it has a reduction potential of 0 volts. That is a defined value. Sometimes it will act as the cathode. So sometimes the standard hydrogen electrode will act as the cathode, and if it acts as the cathode, then that's where it's getting reduced. So hydrogen ion is getting reduced to form hydrogen gas. And then sometimes, so here is that reaction. Sometimes it will act as the anode, and if it acts as the anode, what we'll find is that hydrogen gas will get oxidized to form hydrogen ion. For it to be the standard hydrogen electrode, we need to have everything at standard conditions, and standard conditions requires that anything that is in solution will be 1 molar, and anything that is a gas will be 1 atmosphere. And so that's why you see the 1 molar and the 1 atmosphere there. What we'll find is that this works marvelously, that the platinum is really good at absorbing that hydrogen into the surface and making this reaction possible. So that is our standard hydrogen electrode. So we want to calculate standard cell potential. So I want to teach you guys how to calculate standard cell potential, and we're going to start by looking at, let's see, we're going to start by looking at, we're going to look at 2 different ones, and then we'll do a couple of in-class assignment problems. The standard cell potential is easily calculated. You just need the reduction potential for both the anode and the cathode, and you'll take the difference, so the reduction potential of our cathode minus the reduction potential of our anode. So let me show you an example. So here we've got copper 2 going to copper metal, and zinc going to zinc 2. So this is that very first reaction that I showed you when we started the chapter on voltaic cells. So zinc reacts with copper 2 ion to give us copper metal plus zinc ion. So whichever reaction where the reduction is occurring, that is the cathode. And you'll see here copper 2 is getting reduced to form copper metal. So that means this is the cathode. And then here we've got zinc is getting oxidized to form zinc ion. So that means zinc, the zinc electrode is our anode. So when we do our calculation, we'll do the reduction potential of our cathode minus the reduction potential of our anode. So one thing that I like to point out here is that even though the reduction potential of zinc, we use the reduction potential of zinc, even though it's the anode where oxidation occurs. If you go look on Appendix E, which I'm going to go back to Appendix E now, and we're going to scroll down here and we're going to zoom in on zinc. So there is zinc. You'll notice that zinc has a reduction potential of negative 0.763 volts. So when I go back over here, So it's the 0.763 volts. Well, that reduction potential, here, let's go back and look. That reduction potential was for the reduction. Of course, that's how reduction potentials work. However, we wrote down that reduction potential even though this is an oxidation. And the reason that we can do that is because of this minus sign. That's how we take care of it. So since we subtract away the reduction potential of the thing that's getting oxidized, that takes care of the sign. One thing I want to point out is when you're doing these, make sure you watch out for the minus and minus. Just make sure you're entering that in your calculator correctly so that you don't make any mistakes. All right, so now let's look at another one, and I picked one that has different stoichiometry, and I picked it on purpose for this. So you'll notice here we've got zinc metal plus silver ion gives us zinc ion plus silver metal. Well, in this reaction, zinc is getting oxidized, and so therefore it must be the anode, and that means that silver must be the cathode. So we'll write down these two half reactions. So silver ion plus an electron gives us silver metal. That is our cathode. If we look on our appendix, we'll see that that comes out to 0.799 volts as our reduction potential. Here, zinc was getting oxidized, so it's the anode. So zinc is getting oxidized to form zinc ion plus 2 electrons. Now, in order to calculate Ecell standard, we'll do cathode minus the anode. So we're going to take this number and subtract that number. So 0.799 volts minus negative 0.763 volts. And that gives us 1.562 volts. Now, one thing that I want to point out here. So even though the silver half reaction was multiplied by 2 before we can add the two equations together to give this, we didn't multiply the reduction potential by 2. And the reason that we don't multiply that reduction potential by 2 is that cell potential, it's the potential energy per unit charge, and that is independent of the stoichiometry. In other words, that is an it's an intensive property, so it's independent of the amount. The amount is already baked in because it's joules per coulomb. Okay, so I don't want you to fall into the trick of, oh, I doubled this, I need to double this. That is incorrect and not a mistake I want you to make. So let's look at number 31 and 33. So we'll go over to the in-class assignment and we'll do 31 and 33. So here's our voltaic cell. We've got aluminum plus chromium 3 gives us aluminum 3 plus chromium 2. And we've got some interesting stoichiometry there, but we want to find out what is the anode, what is the cathode. I'll start by writing the oxidation states. That's always a good place to start. Aluminum here is neutral, so that's 0. Here we've got 3 plus, so that's a plus 3 oxidation state for chromium. Aluminum is plus 3 there, and then the chromium here is plus 2. So we'll see that the anode is where oxidation occurs. Well, aluminum is getting oxidized. It's going from 0 to plus 3. So that is the reaction that is occurring at the anode. So we'll put Al solid getting oxidized to form Al 3 plus Aq. And then, so aluminum, and then we'll add the electrons here. So plus 3 electrons there to balance out that half reaction. For the chromium, we've got chromium 3, so Cr3 plus Aq, and it is getting converted into chromium 2 Aq. Well, the only thing we need to do here is to add an electron to the more positive side, and so I'm going to add one single electron there. Now, of course, before we add those two equations together, we would have to triple this, but we don't want to triple the reduction potential. So we don't want to triple the reduction potential when we do that. Okay, so we need to find these reduction potentials. We're going to go over to Appendix E, and I'm going to open that up on Appendix E, and we'll look up aluminum and the chromium. So I'm going to scroll up here. Here is aluminum. So aluminum 3 plus 3 electrons, negative 1.66. So E reduction is negative 1.66 volts. For chromium, let's scroll down here a little bit. So we've got chromium 3 going to chromium 2. Well, there's a chromium 3, but that one's going to chromium 0. Here, we want this one. Chromium 3 going to chromium 2, negative 0.41. So I'll write that down. E reduction is equal to negative 0.41 volts. So negative 0.41 volts. Okay, so now we're going to go, you know what, I just realized I was showing you guys this, but you didn't see it. All right, here, I'm going to show you where I found this. So here's aluminum at negative 1.66 volts, and then chromium, we come down here, chromium 3 going to chromium 2, negative 0.41 volts. All right, well, I forgive myself. All right, so we're going to come back over here. We'll come back over here, and so now we've got those numbers. We've got our reduction potentials, and we're going to do cathode minus the anode. So Ecell standard is going to be equal to the cathode minus the anode, so negative 0.41 volts minus negative 1.66 volts. And we will write down the answer to that, and that is a pretty easy answer. Get ourselves a calculator here. All right. So we'll do, clear all that. We'll do negative 0.4. I'm going to clear that again. So negative 0.41 minus negative 1.66. And that gives us 1.25. So 1.25 volts. And that is our potential. All right, I'm just checking my key to make sure that I didn't goof anything up. All right, so now sketch the voltaic cell, label the anode and the cathode, and give the sign of each electrode. So we're going to sketch the voltaic cell, and so I'll draw an anode compartment here. And we'll give a little space here, and we'll do the cathode compartment there. And here is our cathode compartment. And then in our anode compartment, this is aluminum. So aluminum is our electrode there. So we will have an aluminum anode. And a little crazy there. Let's try that again. All right, so there's our aluminum anode, and I'll put AL. So it is that is our aluminum anode, and that solution. So there's a liquid there, and that solution is going to contain aluminum ion. So it will have aluminum 3+ ion. The concentration of that aluminum ion is going to be 1 molar, and that's because it is at standard conditions. All right, there is something else in there. it doesn't indicate what the counter ion, probably something like nitrate. All right, and then over here we're going to have an electrode that is in this compartment, in the cathode compartment. But you'll notice that the chromium here, chromium 3 is aqueous and chromium 2 also aqueous. Oh, there it is. So chromium 3 and chromium 2 are both aqueous, and that means that, scoot back a little bit here so I can get all of that in. So that means that we don't actually have chromium metal as our electrode. In fact, if we tried to put chromium metal, we would get a very bad result. So instead of chromium, we want to pick something that is inert, and typically when we pick something that is inert, we use platinum. So we'll use a platinum cathode. And we'll just call that PT, so platinum cathode. All right, and then in solution, we're going to have chromium 3 and chromium 2. So I'll put, so chromium 3 plus AQ 1 molar, and chromium 2 plus AQ 1 molar. Okay, and then we've got this, let's see, this is our wire, and we've got some sort of multimeter here. We know the potential is equal to 1.25 volts. And then there is our wire, and it's connected up. Since electrons are coming out of the anode, we'll call that that is the negative electrode. And since they're going over towards the cathode, that is the positive electrode. The direction of electron flow is up the anode, through our circuit, and over to our cathode. Okay, and then finally, here we've got, we need a salt bridge. So I'm going to draw a salt bridge. And a salt bridge can be made out of any number of things. So there's our salt bridge. And that connects everything. So let me make sure I have it. Sketch the voltaic cell, label the anode and the cathode. So there's the anode, there's the cathode. Give the sign of each electrode, negative and positive. We did that. And indicate the direction of electron flow. We did that. So there we have drawn our entire diagram here for that particular electrode. So we want to look at number 33. So we want to look at number 33. And for number 33, it says using standard reduction potentials, Appendix E, calculate the standard EMF for each of the following reactions. Well, the way to do this is to write down the half reactions. So we're going to take here, we've got chlorine going to chloride. So we've got Cl2 gas, and that is getting converted into 2ClAQ. And so here, to balance the charge, we'll put the 2 electrons on the left, and that tells us that must be our cathode. All right, so that is our reduction. That must be our cathode. And then let's write down the other one. So we've got 2 iodide, AQ, and it is getting converted into iodine, solid. And to balance the electrons there, we'll need the 2 electrons on the right side, and that tells us that this will be the anode. That will be the anode. All right, so that's our cathode, that's our anode. We now want to look up our reduction potential for each of these. So we'll look up the reduction potential. That's going to be in Appendix E. And so chlorine, let's see. There's chlorine right there. So chlorine plus 2 electrons gives chloride. That's 1.359. So I'm going to write that down. 1.359 volts. And then for iodine, here it is. although we have the oxidation, we're just going to write down that number. So 0.536 volts. So 0.536 volts. And then Ecell standard is equal to the cathode minus the anode. So 1.359 minus 0.536 volts. All right, so it's just a matter of punching those numbers in. So 1.359 minus 0.536. And that comes out to 0.823. So 0.823 volts. Okay, so on this next one, we've got iron, iron, and more iron. Well, clearly that is kind of weird. So in order to deal with that, we have to figure out, well, this iron is going to iron 2, and this iron 3 is also going to iron 2. So we're going to write that down as two separate reactions. So we've got Fe solid that is getting converted into Fe2 plus Aq. All right, in order to make this work, we'll have the two electrons that are there. And since that is oxidation, that is going to be our anode. All right, and we will put our reduction potential there. And then for our other one, we've got Fe3 plus Aq, and that is getting converted into Fe2 plus Aq. And so 3 plus and 2 plus, and we will put an electron there on the left side. And then we'll have E, reduction potential is going to be that. So since that one is actually getting, that's a reduction, that one's going to be our cathode. So that one is our cathode. All right, so we need to go look up these values for iron. Fortunately, they're going to be right next to each other. And let's see. So there's the iron. Scoot over. So we have iron 2 plus 2 electrons, because that one's negative. I'm going to write this down. So that is negative 0.440. So negative 0.440 volts. And then our iron 3 to iron 2 is positive 0.771 volts. So we're going to come back over now. So we'll come back over here and we'll do cathode minus the anode. And so Ecell standard is going to be equal to 0.771 volts minus negative 0.440 volts. So 0.771 minus negative 0.440. And that gives us 1.211 volts. And that is going to be our cell potential for that one. All right, well, we've got another one here. Let's go ahead and get it done. So we've got aluminum 3 plus Aq is getting converted into aluminum. So I know the electrons are going to be on this side. So that gets it converted into the aluminum solid. And that's going to take 3 electrons to do that. And since that's the electrons are on the left side, that tells us that that is the cathode. So I'm going to go ahead and write that down. Our cathode. And then got a reduction potential. I don't know what that number is, so we'll have to look that up here in just a moment. And then our other one is calcium is getting converted into calcium ion. So we'll get Ca2 plus Aq. And then here, to balance this, we'll need 2 electrons there. And our reduction potential is going to be some number that I don't remember. So we'll come back over here. We'll switch back over to this screen. And we've got them both right here. So the aluminum is negative 1.66. So negative 1.66 volts. And the calcium is right here at negative 2.87. And that's a pretty negative number there, negative 2.87 volts. And so we'll go back. And now that we've got that, and just as a reminder, since this is the oxidation, the calcium is going to be the anode. So that's going to be our anode. So now we'll do cathode minus anode. So Ecell standard is equal to negative 1.66 volts minus negative 2.87 volts. All right, so negative 1.66 minus negative 2.87. And that gives us 1.21 volts. So 1.21 volts. All right, so let's go ahead and go on to the next thing. Normally I wouldn't do the video this long, but you guys can pause it whenever you need to. So we'll go on to the next part. If you have if you've got a spontaneous cell, then Ecell is going to be greater than 0. If you know that the cell is supposed to be spontaneous, then the cell potential will be positive. So your cell potential will be positive. When we look over here, that means that in order to make the cell potential positive, then your cathode needs to be the more positive or less negative reduction potential. As we saw with the calcium and the aluminum, that one we just had, the aluminum was the less negative reduction potential. But it's either the more positive or the less negative reduction potential. Now, just as a quick note, it is possible for a cell potential to be negative, but what that means is that the reaction is not going to be spontaneous in the forward direction. It'll actually be spontaneous in the reverse direction. And so that's roughly the equivalent to having a delta G that was greater than 0. It can happen, and we can write out equations that correspond to that. However, that is going to be that is going to be an issue. So just something to think about when you're doing this. Okay, so so now we've got we want to do number 37. So let's go back over to number 37 on the in-class assignment. Here is number 37. So we've got a 1 molar solution of copper 2 nitrate is placed in a beaker with a strip of copper metal. And a 1 molar solution of tin 2 sulfate is placed in a second beaker with a strip of tin metal. And the 2 beakers are connected by a salt bridge, and the 2 metal electrodes are linked by wires to a voltmeter. So here's the thing. We don't know which one is going to be the anode and which one is going to be the cathode. And the way that we're going to determine this is that we're just going to look up the values. So let's write out the equations first. So we'll have copper 2 plus AQ plus 2 electrons gives us copper solid. So copper 2 going to copper solid. The other possibility for the cathode would be SN2 plus AQ plus 2 electrons, and it would go to give us SN solid. Either one of those potentially could be the cathode, And we won't know unless we go look up the reduction potential. So I'm going to write down here E reduction standard, E reduction standard, and we're gonna go look those values up in appendix E. All right, so we'll start with copper. Let's see, there's copper right there. So I'll need to zoom over. Oh, try that again. So copper 2 plus an electron. We're going to need to go up just a little bit more. Copper 2 plus 2 electrons gives us copper metal, and that one is 0.337. So 0.337 volts. And then for tin, I'm not sure where SN is. It's got to be down here. There it is. SN2 plus 2 electrons gives us SN, and that's negative 0.136. So negative 0.136 volts. All right, so now that we've written those down, we can tell which one of these needs to be the cathode, and therefore also which one needs to be the anode. So the one that is more positive is going to be the cathode. So I'm going to go ahead and write that down. So this is going to be our cathode. So either more positive or less negative, and that means the tin is going to be the anode. All right. So, so since copper is going to be our cathode, we're going to rewrite that equation exactly like it is. So, so we've got copper 2, AQ, plus 2 electrons, gives us copper solid. And for tin, it's going to be the reverse. Since it's the anode, it's actually going to be the oxidation. And so that will be SN solid, and it'll get oxidized to form SN2 plus AQ plus 2 electrons. And then when we add those two equations together, our overall equation is going to be copper 2 plus AQ plus SN solid gives us SN2 plus AQ plus copper solid. And that is our overall cell reaction. So which electrode gains mass and which electrode loses mass as the cell reaction proceeds? Well, you'll see that copper goes from ion to solid, so copper will gain mass. As the reaction proceeds. So copper will gain mass, and the tin, so tin goes from 0 to plus 2, so we're losing some of those into solution. So tin will lose mass. All right, and then finally, what is the EMF? Here we just want to do cathode minus the anode. So Ecell standard is the EMF, and that will be 0.337 volts minus negative 0.136 volts. So 0.337 minus negative 0.136. And that gives us 0.473 volts. So 0.473 volts is our answer. Okay, well, we've got one topic left in this video, and I know we're at almost an hour on this video, but again, you can pause it at any point that you need to and take a break. All right. So next, we're going to look at which is the stronger oxidizing agent and which is the stronger reducing agent. For this, we've got, let's see here, we've got the stronger oxidizing agent, stronger reducing agent. So here is how this works. The more positive the reduction potential, the stronger the reactant is as an oxidizing agent. So on that chart that I showed you earlier, fluorine had a very large positive reduction potential. It was like 2.87. And that means that fluorine is the strongest oxidizing agent. Not surprising if you've paid attention as we've gone along here. Fluorine is the meanest, baddest, most electronegative element on the whole periodic table. Not surprising, it's the strongest oxidizing agent. Then we'll find the more negative the reduction potential, the stronger the product is as a reducing agent. And so you might remember on that chart, lithium had a reduction potential, lithium ion had a reduction potential of negative 3.05 volts. Well, that means lithium solid, the product of that, is going to be a very strong reducing agent. Now, I'm going to go back to that chart so you guys can see, just to illustrate this point. So this is that, yes, there we go. This is that chart, shows the reduction potential. And so again, the more positive the reduction potential, the stronger this thing is as an oxidizing agent. So fluorine, great oxidizing agent. Permanganate, strong oxidizing agent. Chlorine, dichromate, oxygen. These things are very good oxidizing agent, with fluorine being exceptionally good. And then we go over here to the negative ones. Well, the negative ones, the more negative it is, the stronger these things are as reducing agents. So we'll find that lithium and potassium and calcium and sodium, those are all really strong reducing agents, with lithium being among the strongest. So we can use Appendix E to calculate which one is going to be the stronger, which one will be the stronger oxidizing agent and which will be the stronger reducing agent. So I'm going to switch back over here, pull that back down, and on this I don't need the calculator for that. We just need this. Okay, so we've got chlorine and bromine. So we're going to look up chlorine and bromine, and I don't know, those are on that chart that I just showed you. So I'm going to go ahead and we're going to use that chart real quick. Chlorine is here it is. Chlorine is positive 1.359. So E reduction. So positive 1.359 volts, whereas bromine is positive 1.065 volts. So now when we come back here, since chlorine has a larger positive reduction potential, that means chlorine is the stronger oxidizing agent. So the more positive, the stronger the oxidizing agent. Okay, I think we're going to have to break out the full Appendix E because these are there's just not all of them on here. So, all right, so bromate and iodate. Let's see, there is bromate right there. That's the one we want at 1.52. So I'm going to go ahead and write that down. 1.52 volts. This is our reduction potential. And then iodate, ooh, it's right there, 1.195 volts. And while I'm here, I'm going to get peroxide, AQ is right there, 1.776 volts. And then, oh, look, it's right there. There's 1.776 volts. And then ozone, let's see, ozone. It's down on that next page. Over here, there's ozone at 2.07. All right, and that also is volts, so reduction. So now let's go back over here, and you'll see bromate was 1.52 volts, whereas iodate was 1.195 volts, so the bromate is the stronger oxidizing agent. And then here, peroxide is a really good oxidizing agent, but ozone is even better. So at 2.07, that's going to be a stronger oxidizing agent. Now for these, we're going to do the opposite. We're going to look at the reduction potential, but the one that has the most negative, the thing that has the product where it's the most negative, that's going to be our stronger reducing agent. So let's see. All right, iron and magnesium. Generally speaking, if you're just looking at metals, the further to the left it is, the stronger it will be as a reducing agent. So magnesium is a pretty good bet here, but we're going to go back over to, here. So we have iron and magnesium. We need to go up. So there's iron. Iron's right there at negative 0.440. So negative 0.440 volts. And then magnesium, there's magnesium at negative 2.37. So negative 2.37 volts. That means, so we'll come back over here. That means, so with iron here at negative 0.440 and magnesium at negative 2.37, that magnesium is going to be the stronger reducing agent. All right. So for calcium and aluminum. So there's calcium at negative 2.87 volts. That's pretty strong, hard to beat there. And then we'll go back up here. Here's aluminum at negative 1.66. So negative 1.66 volts. So here we go. So calcium at negative 2.87, aluminum at negative 1.66. Calcium is going to be our stronger reducing agent there. So now, just got one more. So hydrogen, I know this one without even looking it up because that one is by definition going to be 0, but there it is, that one's 0. So hydrogen is 0 volts. And then H2S, so we want to find the H2S. So I think we're going to have to come down here, H2S. There is H2S on the right side, so positive 0.141. So 0.141 volts. So 0.141 volts. And now we'll come back over here. And we'll look at the numbers, 0 versus positive 0.141 volts. The more negative, the stronger it is as a reducing agent. So 0 is going to be better than positive 0.141. And that will give us our strongest reducing agent. All right, we're going to, let me make sure here. Yes, we're going to stop there, and our next video will start on section 20.5.